Now that we have covered chemical reactions and how they happen and the types of chemical reactions that can happen, we need to cover how energy is involved in chemical reactions. We have 3 learning objectives for today. The first one is that you be able to distinguish between endothermic reactions and exothermic reactions. So you're going to need to be able to tell the difference between those two. Then you're going to need to define the term activation energy for me, so be on the lookout for that as we take notes. And you're going to need to be able to identify ways to increase the rate at which a reaction is happening. So essentially the speed at which a reaction is happening. You'll need to find ways to make it go faster. Let's jump right in then and talk about energy. All chemical reactions involve energy being absorbed and energy being released. This is because breaking chemical bonds, which has to happen in order for a reaction to start, involves absorbing energy from the surroundings. You have to have energy to break a bond, and it's going to come from the surrounding materials. When you form new chemical bonds, which happens at the end of every chemical reaction, then energy is released because forming bonds makes the elements more stable and they release energy as a result of that. However, not all bonds contain the same amount of energy. A bond that forms between a hydrogen atom and a hydrogen atom is going to have a different amount of energy than the bond that forms between a hydrogen atom and an oxygen atom. So it's possible that the bonds you break to start a chemical reaction will have more energy or less energy than the amount of energy that's released by the bonds that form at the end of the reaction. As a result, chemical reactions are going to fall into one of 2 different energy categories. The first energy category is an endothermic reaction. In an endothermic reaction, overall energy is absorbed. What this means is that more energy is absorbed by the breaking of the bonds than is created by the forming of the bonds of the products. So, breaking the bonds to start the reaction happening is going to require a lot of energy, and not a lot of energy is going to be released when we make our new bonds at the end. So, overall, the reaction is going to take energy in from the surroundings. This means if you're going to keep an endothermic reaction going, you have to constantly be adding energy to it. You can't just start the reaction and then let it run on its own, because it won't continue, because the energy released at the end isn't enough to keep the reaction going. You have to keep putting energy in order to keep breaking the bonds that start the reaction so that it can continue. Many endothermic reactions feel cool to the touch or even cold to the touch because they're taking energy from their surroundings. Remember that what we feel as heat is really just a transfer of energy. So when something feels cold, what it means is it's removing energy from your hand. And that energy, in the case of this reaction, is being used to fuel the reaction continuing happening. The second category that reactions can fit into is called exothermic reactions. Exothermic reactions overall release thermal energy. This means that when you break those initial bonds, energy is still absorbed, but the bonds that form at the end release so much more energy than what's taken in to start it that overall the reaction releases energy. Once you start an exothermic reaction, it will continue on its own because you'll put in a little bit of energy to break those bonds to start, and then the formation of the new bonds releases so much energy that it fuels the breaking of the bonds to start the reaction again, and you don't need to put more energy in. So a good example of this is a fire, right? If you light a fire with a match, you put in a little bit of energy and you get back a lot of energy. And you don't need to keep lighting the wood over and over and over again for the fire to continue. It just burns. Many exothermic reactions are going to feel warm to the touch because they are releasing energy into their surroundings. So now let's talk about activation energy, because activation energy is something that is needed for every reaction to happen. Remember that we said all chemical reactions begin by having bonds broken. And in order for bonds to break, we have to have energy put in. That energy you put in to break the bonds the first time to start off this reaction is called activation energy. And there's a different amount of activation energy required for every reaction that happens. Reactions that appear to happen on their own must have really low activation energies, because no reaction happens spontaneously without an input of energy. So if something like rusting is happening seemingly without anybody helping it along, all that means is that the activation energy required to start it is so low that just heat from the world around it can start it happening. The opposite of that would be reactions that have high activation energies. They require energy to be put in, but then they will begin. Exothermic reactions, even though they release energy as a whole, still require energy to start them, but then they wind up releasing a ton of energy in the aftermath. So to start a fire, you got to put energy in, you have to light it. But once you light it, it produces a lot more energy than you put into it to begin with. So just because something's exothermic or because something appears to be happening on its own doesn't mean that it doesn't require activation energy. All chemical reactions have an activation energy. Let's talk about reaction rates. Reactions of all different kinds happen at different speeds. So some things happen very slowly, like rusting. That happens so slowly that you can't just sit there and watch your bike rust. Whereas a firework explosion takes place in a matter of seconds. Wildly different speeds for these chemical reactions, right? The speed at which a reaction takes place is called a reaction rate, and it can also be affected by different factors in the environment. And those factors that we're going to talk about are surface area. So surface area is just the amount of exposed outer area of a solid. So think about a solid cube of aluminum. You have just the outside surface of that aluminum that's exposed to the air. If you wanted to increase the surface of the area of the aluminum, you could use something to shred it up into thousands of little pieces, right? Like a file where you shave off all these tiny little shavings. And now every single one of those shavings has an outside edge that has more surface area to it. Well, if you increase the surface area that is exposed to the chemical reaction, you'll actually increase the rate of the reaction. Now, why is this? Well, it's because as you increase the surface area that can come into contact with each other, then you wind up having more collisions, and the more times you have collisions, the more likely it is for bonds to be broken and for the reaction to take place. Temperature also affects reaction rate. Remember from previous chapters that temperature is just a measure of the average kinetic energy that a particle in a substance has. If you increase the energy of the particle, which is increasing the temperature, you're going to increase the rate of the reaction. This is because particles are going to run into each other more often. Again, more chances for bonds to be broken. And when they do run into each other, they'll also have more energy, which means more energy, more likely bonds will break and reactions will start. Increasing concentration, or the amount of particles in a substance in solution, will also increase the rate of reaction. So think about if you have a solution that only has a pinch of salt in it as opposed to a solution that has a whole cup of salt in it. You have so many more salt particles to run into other particles and have a reaction. More particles, more collisions. More collisions, more reaction happening. For gases, it's not as simple as just pumping more gas into a space, but if you increase the pressure on the gas, that will increase the concentration, and again, increasing the concentration increases the rate of reaction. Let's talk about one more way to affect the rate of reaction, and that's by using a catalyst. A catalyst is a substance that can increase reaction rates, and it can do it by lowering the activation energy of a reaction. So it can actually make it so you need less energy in order to start the reaction. Sorry, my baby's sick. One way that catalysts can lower activation energy is that they can actually cause reactant particles to collide with each other more often, which is going to mean they are more likely to react. So that lowers the energy needed to start the reaction. Some important things that you have to know about catalysts. They are not changed or used up during the reaction. So unlike reactants that combine with each other and are used up and are not there at the end of the reaction, catalysts aren't changed. They're not actually participating in a chemical change. They're just helping speed it along. They also don't change the reactants or products. So by putting a catalyst in there, you're not going to have a new reactant or a new product that you didn't have before. They also won't increase how much of a reactant is used or how much product is produced. So using a catalyst doesn't guarantee that you will have more product at the end of your reaction. And they aren't considered reactants. They're not actually participating in the reaction. They're just changing the speed at which it happens. Your body uses catalysts all the time. The catalysts that are specifically in your body cells are called enzymes, and they're used to speed up the chemical reactions that otherwise might be taking too long to support life. So you use an enzyme called protease to help break down proteins that your body needs in order to have energy to fuel it. If that process took too long, you wouldn't get enough energy and you wouldn't survive. There's a molecule that's the opposite of a catalyst, and it's called an inhibitor. Inhibitors slow down reactions, and sometimes they stop reactions altogether. Inhibitors are important because you find them in lots of medications. Medications that are designed to stop bacteria will often have an inhibitor in them, and that inhibitor stops reactions that bacteria need to go through in order to survive and thereby kills the bacteria. The same thing can be used to help prevent food from spoiling. That is the end of our notes for today. Your homework is going to be the 9.3 Check for Understanding that will be posted on Google Classroom.